Wow, well done for coming so far, but here's the question, have you enjoyed the journey? Okay, you can do everything now, I think. We started off down here with McDonald's signs and things to try and get familiar with this parabola, or the quadratic function. And then we did some investigations, what the formula was like. We moved it around, some transformations, and then, of course, it came time to look at getting the turning point form, or the vertex form, or maybe doing it over here without that form. And can you do all that stuff? I don't know. Well done for trying. Let's see if we can pull it all together here and have a look. So, you have the power. I hope you have the power. Hang on, we just lost the power, mate. Let's back up here. I hope you do have the power. We had a look at this summary before. I want to go back now and give it a tick if you think you can do it. So here, a quadratic equation with a positive coefficient of x squared. What is that? ax squared plus bx plus c. So that's your quadratic function. If the number in front of x squared is a positive, it is concave up, or we call this convex. Okay, the cave is on the top. If it's got a negative coefficient of x squared, I want you to use this as a checklist. Have you the power? Let's get the power now. And if it's negative, it's going to be concave, or concave down. How do you know it's a cave? There you are, you're in your cave, mate. I made a little cave for you there. That's the way you remember that. Okay, what about the y-intercept? How did we do that? All on the y-axis, x is naught. So plug x is naught into the function, and what do you always get? A times naught squared would be naught. B times naught would be naught. Y will always be the number down the end. How about that? Not bad. Hey, you don't need to worry about a calculator anymore. You have the power, the mathematical power. So the x-intercepts, of course, is the axis. Y will be naught. We spent a lot of time on these. It could be no x-intercept like that one. Or what about one like this? One x-intercept where it actually touches, or two x-intercepts. Okay, so what do? You put your function equal to naught, and then you invoke the null factor law, and you try to factorise it. Okay, if it doesn't factorise, you can use the perfect square form. Okay, put it in a perfect square form, and then go on with that. Do you remember that? Difference of two squares and stuff. Okay, so we did that. So we have these three conditions. No solution. There's one solution, the parabola touches the x-axis. That's when you get something like x, what's this? X take 3 squared. Okay, something like that. And you would have x is 3 twice. And therefore, just that one touching point, a repeated factor there. But you're doing that a bit later on in your mathematical career, but we can notice it now. What about the turning point? Hey, that's sort of where we started, with a translation of x squared by h in the x direction and k in the y. Can you do it? Do you have the power to put functions into a perfect square form? Might have to go back and revise that. That was the last presentation, if you remember. Okay, here we go. When a graph has two x-intercepts, there and there, it might be concave like this, or convex. The corresponding, here we can say the corresponding y value. So if there's these two here, like we've said, we've seen this before, the vertex is on the axis of symmetry here, halfway between the two x-intercepts. So, if this was 1 and this was 5, you could add them up and say halfway between was 2, so that's the x value, oops, I think it's 3, mate, 3, and that would be the x value of that vertex, halfway between. And now to get the y value, you could substitute the x value back into the equation, okay, and get the y value in there from whatever your formula was. So that's something we want to practice now as we pull all these ideas together. There's a couple of ways of finding the vertex. You could actually complete the square, can't you? Come back up here to this form over here. Okay, but if you don't like doing that and you've got two X-intercepts, you could actually add those two X values, find the X value in the middle, and you'd have the X value of the vertex. So study that one. We're going to practice that in this next set of exercises. Okay, when a graph has only one X-intercept, the turning point is the X-intercept. It sits right on there, like we've discussed up before. Okay, so the axis of symmetry they quite often ask you for, and that's always X equals some constant going through there that is the line of symmetry of the parabola. Okay, let's go on and have a look. Here we are. You've been waiting, haven't you, budding young mathematicians? Why does it all work? Let's have a look. Why is it so? When you have y equals ax squared and you change a, why do you change the steepness, or why is this a dilation, or sometimes we call it a stretch? How does that work? Let's go back to a table of values. There's some x values, and when I square them we get these. Now let's use 3 in there. Now, what's happened? X squared is -2 squared down here is 4. Now, let's take that one. -2 squared is 4. But I'm going to actually multiply it by an a value of 3. 4 becomes 12. Uh-oh, I think I can see the stretch happening. Goes up to here. Okay, can you see it? Each value of x squared, when you get x squared, here's an x1, you multiply it by 3. Naught will stay at naught though, so it will stretch from that point up. 1 squared is 1, then you multiply it by 3. It's going to go 3 times as high. Okay, so it's a little bit too high there, 3. Okay, 2 when you square it is 4, that's x squared, then you go and multiply it by 3. So here that goes to there, oh, goes up to 12. Can you see it? Do you understand the effect of that? Let's look at the next one. Y equals x squared plus a. This is a what? Y translation, or translation in the vertical direction. Okay, why does it work? Let's have a look. -3 when you square it to get x squared is 9. If you add 3, you get 12. So let's do that one. 3 is going to map here to 9. Uh-oh, you're adding 3, going to be 12 there. Let's do another one. -2 when you square it is 4. Okay, and then when you add 3 is 7, so 4 goes up to 7. Can you see all the points are moving up by that a value, which here I've used as 3. They're all moved up by 3. Okay, the gap there is always the same. It is a vertical or y translation. Okay, what about this one down here? This always puzzles students. X plus a squared, and why does it move in the opposite direction to the sign of a? Okay, this is a X translation or horizontal translation here, produced by this change, x plus a. So what have I done here? I've made up a table tracking x plus 3 squared. Let's track it now. When x is -3, x squared is 9. Okay, so this is the blue one here. Okay, -3 is 9. That point is what we're interested in. Now, let's do it differently. Before we square the x, we've got to add 3. -3 plus 3 is 0. So -3, this is y equals x plus 3 squared here. It's 0. Okay, how did that happen? Let's do it again. -2 squared is 4. Okay, so that's there. Now, let's not do that. Let's have x plus 3 squared. So we have to put -2 plus 3 and then square it. So we're actually adding 3 onto it. -2 plus 3 is 1. 1 squared is 1. Hey, they're all across to the left, right? Opposite to this plus 3. Can you see why that is so? Let's see if we can work it out. Well, when you take an x value, let's take one up here now. when you take x is 2, it usually gives 4. Okay, but we have added 3 to it, so the x equals 2 now behaves like an x equals 5. Okay, so x equals 2 now is way up here somewhere, up at 25. So each of the x values is behaving as if they are 3 bigger than usual. Okay, so what are we doing? Let's go back to this point. This is neg 3. When you add 3, you get 0. So neg 3 is behaving as if it was 0. And 2 is behaving as if it was 5. Because before you square it, you add 3 on. So therefore, the whole graph occurs earlier. So the usual graph here, the usual x values in blue, will occur for smaller x values. It'll be to the left because you add a number before you square it. Okay, so you only need a smaller x value here. Okay, do you get it? You can do the same thing with x take 3 all squared. You will need bigger values over this way because you'll take 3 away before squaring it, before you produce the usual x squared value. So that's a way of trying to understand it. Okay, so you might try to think about that. Do you want to do some slightly heavier mathematics? Here you go. Let's do the formal proof now. Let's do it with transformation equations. So what we say is we start off with y is any function in x. And we're going to translate it, translate points A in the x direction and B in the y direction. And we want to see what happens. So what we're going to say is our new x, call it our new x, is our old x plus a. We're going to add a to all the x's, and our new y is going to be y plus b. We're going to add b to all our old y. So we're going to move it. Let's have a look at what we're doing here. Whatever the curve is, let's say it's this. We don't know. It could be any function. We're not saying it's just a quadratic. It could be any function. So we're going to move every point a that way and b that way. Let's imagine that they're both positive. Perhaps it could be negative. Doesn't matter. So every point's going to be moved across. What's going to happen to the formula for the function? Let's look at it. Rearranging these equations, we can say the old x, subtracting a from both sides, is the new a minus the a, new x minus a. The old y is the new y minus b. So that's rearranging those to get the old x and the old y as subject to the formula. Why might we want to do that? Well, let's take these and go back and look at what happens to the original function. So the original y is going to be replaced by this. Y prime new y minus b is f, and it's not going to be f of x. It's going to be f of old x is the same as x prime take a, the new x take a. Let's rearrange that. My new equation is my new y equals f of new x minus a, substitute into the function, plus b. Ooh, you have the whole story now, don't you? If you translate up here, if you translate all points on the plane, your old formula now in the x hole will have x minus the direction of the translation here, x minus a, but the b on the end will be the same direction as the translation. How did that happen? What's the algebra here? Let's have a look. Back up here. It's going from here to here. You're moving it plus a, but when you rearrange to get the old x in terms of the new one, you move the a across the other side. It's x prime take a. Okay, and that journeys right through to stay in the function there as the opposite sign. This is fairly heavy mathematics for this level, I suppose. Now, why doesn't the b do the same thing? Could you do the same thing? Okay, you replace y by y prime or new y minus b, but then conventionally you put it back on that side so you have a explicit statement for your new y. So the y moves like the x does, the translation value, but it moves back again because of the transposition of those terms. Heavy stuff. This is the transformation, if you like, proof of this result. So this result says it doesn't matter what the function is. Let's take y equals x cubed, and let's translate it. Let's put it this way. Translate it, 2 in the x and 3 in the y. What this says is that the new formula will be y equals x take 2 cubed plus 3. Notice, we're not doing this just for quadratics. It could be any f of x function. Let's take perhaps a different one. What's another function that we could do? Well, let's just do another power. X to the 4th will become y equals x take 2 to the 4th plus 3. Okay, what a powerful tool, because if you know your basic shape, x squared or x cubed or x to the 4th, and you want to translate it, you can quickly, using this transformation equation approach, come to the new equation. It's one of the most powerful little results in mathematics, actually. It's very powerful because you can sketch many, many other functions by looking at that form. All right, that's not in the course, but it's interesting for you to think through that, I think. All right, so let's go on and have a look. Let's do some examples from Pearson's now. And so what we're going to do is we have the power, and we have the power to do everything about the function. So let's see if we can do it for this function here. We want to find the shape. Okay, so you see it's a positive x squared, so it's a parabola which is convex. Okay, learn that word. Or concave up. Now, where does it cut the y-axis? Let's do that one next. So when x is 0, you put 0 in, and you always get the number down there, 0.8. Then you should always state your answer as x is 0, y is -8. A full point, a pair of coordinates make a point, not just the y value. Finding the x-intercept. We've done a lot of this. Put y as 0. There it is. I will use the null factor law. So we need to factorise it. X by x is x squared. Plus 4 by -2 is a -8. And it ends up with a plus 2x term. We've got to do a bit of trial and error there. Then by the null factor law, the first factor is 0 or the second is 0. Therefore x is -4 or x is 2. Make up the complete points. -4 and 0 because it's on the x-axis, y is 0. And x is 2, y is 0. Make up a complete point for the intercept. Okay, turning point. Let's use the new tricky-do. What is the x value here? -4. Okay, let's just draw this so you can see what's going on. -4 and 2 is where this graph cuts the x-axis. So it's going to be something like this. And we've said this is down at -8. 0, -8. This is what we found so far. So where would the middle be? Hey, halfway between the x-intercepts, because it's got symmetry of this function around the vertex. So we can find the x value there by adding up -4 and 2 to get halfway. -4 plus 2 on 2. X will equal that halfway. Halfway between two numbers, remember, is the average of those numbers. So here x is -1. But we want the y value of that as well. Well, what's the formula mean? Remember, the formula for a function is the rule that the x and y of points on that curve must obey. So if you know x is -1, well, let's just write the function here. Y equals x squared plus 2x take 8. So if x is -1, put it in there. -1 squared, and then in there. And that, the rule says, the point where x is -1 must have a y as -9. That's the meaning of that rule or equation for the curve. So we've just found this is -9. That fits nicely with -8 because it comes up and crosses the y-axis just there. I've gone too far now, so let's just come back. So, therefore, the turning point, or vertex, more often referred to as the vertex, is that point there. Okay, you could complete the square. Okay, let's do that. Repeat this line, x squared plus 2x. Halve the number in front of x, that's 1, square it and add it on. So that automatically gives you that square. Then you bring the 8 down and also adjust by taking the 1 off, and we get that. Therefore, we know from here, and from the translation approach that we just mentioned before, it's -1, -9. Opposite sign for the x there, from what's in the brackets. And you've just seen the proof of that. Okay, come down and you put it all together. You have the power. You have the power. Okay, this is powerful. Okay, you don't need technology now. You are a budding young mathematician. Go for it. Okay, all those things are marked in there. Here we have these points, have the vertex mark, the y intercept mark, and the axis of symmetry label. Now, do you want to have a freebie point to get the fatness a bit better? Just remember, if this is the axis of symmetry, that at -8, there should be an equivalent symmetrical point the same distance the other side. So you could put that across there and get that point just to get your fatness there a bit better. Okay, that's what I call that a freebie point. Freebie, you don't have to actually calculate it because of symmetry. Okay, that just reinforces the idea that you know this is the axis of symmetry and you can generate points equidistant on either side. Okay, let's go up here and have a look. Let's do it again. X squared plus 2x take 15. Doing everything. Okay, so the first thing is stating the equation. This has got a positive x squared, so it's convex or concave up. The cave's in the top if you like. When x is 0, stick it in again. These two go out. Of course, it's always -15. We discussed this earlier. So the y-intercept is 0, -15. When y is 0, put equal to 0 again. Okay, and they're putting it across on the right because most people read from left to right. It's equal 0, so we want to factorise it and invoke the null factor law. Either that factor is 0 or the other factor is 0. So x is -5 or 3. Make up a proper point, -5 0 and 3 0. A point, remember, has 2 coordinates. Now, they found the turning point here by completing the square. Okay, well, let's look at it. X squared plus 2x, bring them down, and then your wish number, the one to make this a perfect square, halve the number in front of x, which is 1, square and add it on. That bundle automatically forms a square. Now you have to take it off, and just remember you had the -15 there. So that this line must expand to that line, or simplify that line. So down the end here you have -1 take 15 is -16. So the turning point is -1, -16. Okay, do you want to check it with halfway between method? Let's have a look at it. You don't need to draw the graph, but let's have a look. -5 here, and 3 up here. Axis of symmetry somewhere halfway in the middle. We know it's going to go like this. So what's halfway? The x value is -5 plus 3 on 2, which is -2 on 2. So x is -1. Doing it this way. And then sub it back into y equals x squared plus 2x take 15. So putting it in, -1 squared is 1, plus 2 by -1 is -2, take 15. Yes, it checks. -16. Okay, so either of those methods, whatever's convenient. So if, for example, you're given a graph and you've got these, there's a little tricky way of finding the axis of symmetry, isn't there? From the middle point between the x-intercepts will give you the axis of symmetry. So the axis of symmetry, therefore, is x equals -1. The line up here going through the middle. Okay, putting it all together, labelling everything, showing the axis of symmetry with this line and its equation down here, labelling points for full marks. You have the power. Are you feeling powerful? Let's have a look at the next one. I'll just come up here a little bit. Yep, we'll just go to here. Y equals 4 take x squared. Okay, look out. They put the x squared second. Neg x squared. So this is going to be a concave when you've got that negative in front. Remember, it reflects it in the x-axis. Okay, so let's go through the same thing. Y-intercept, put x is 0. 4 take 0 squared is 4. So it's the point 0, 4. Now we're going to put 4 take x squared equal to 0 to find the x-intercepts. And using the form we've got here, it's 2 squared take x squared, which is 2 plus x by 2 take x. Okay, by null factor law, the first one's 0 or the second, so x is plus or minus 2. Either neg 2 naught or 2 naught. You could do this one differently. 4 take x squared equals naught. Therefore put x squared, add x squared to both sides, and then find the square root, so it'll be plus or minus 2. Remember, where you're finding the square root of a number, there are 2 possibilities. A positive times a positive will give 4, negative 2 by negative 2 will give 4. A couple of different options there. Okay, so for the turning point, what have they done this time? Gone halfway between these values, done it that way, and then subbed it in. Okay, the turning point is at 0, 4. There it is there, comes down to 2 and neg 2, and the axis of symmetry is the y-axis, x equals 0. Okay, now that was a rather easy one, because let's look at it. There's many ways of looking at this. 4 take x squared, you could do it differently. You could put the x squared in front. It's neg x squared plus 4. Hey, we could have done that by transformations. There's x squared, multiply it by neg 1, that's neg x squared, then add 4 up there, and we've got that. So we could have gotten that top point. We still need to go and get these. But can you see, you have a powerful knowledge here of this function x squared and all its transformations, all its changes. Okay. Now get flexible here. You have the power, remember. Okay. Sketch the graph of this one. Well, this is pretty friendly because we already know the turning point. So here, what's been done to it? Well, let's first of all say it's neg x squared. Okay, so that's been inverted. No, I prefer to have reflected in the x-axis, so it does invert it. And of course it's moved across 2 and 5. Okay, so we've got a lot of knowledge because of that particular form. Let's try and do that a little bit better there now. So come across here, hard on screen here, to do that. So we've got 2 and 5 up there, and it's neg. So it's going to go through somewhere at, let's have a look in here, through like this. Let's try and, so that's at 2, 5, and it's negative. So let's see if we can put some things in. Find the y-intercept by substituting x is 0. Oh, well, I've got, it's in here somewhere. It goes in there, the y-intercept goes around like that, and now we've got to find the x-intercepts. So where are the x-intercepts when y is 0? So putting the whole thing equal to 0. Okay, putting all terms over there, so neg x take 2 squared becomes x take 2 squared, and take 5 over there, and so now you have difference of 2 squares, that squared minus root 5 squared equals 0. So it's the first plus the second, first minus the second, and then we therefore can rearrange it and get 2 take root 5 or 2 plus root 5, or we can package it up like that. Okay, now when you do this rearrangement here, x take 2 squared take 5 equals 0. You can use the difference of 2 squares, or you can do this. Right, get the bracket by itself, then take the square root of both sides, plus or minus root 5. Don't forget 2 conditions. Then you add 2 to both sides, so it's 2 plus root 5, or 2 take root 5. Okay, so that one wouldn't have factorised even if it was expanded. So what's this? This is 2 take root 5 0, and this is 2 plus root 5 0. So not nice numbers there, not rational. They're third form when you have that square root sign. Okay, so do you get it? A couple of different ways you can do that then. Alright, so you could use your calculator now to find approximate values to help you plot those 2 plus root 5 and 2 take root 5. So here on the sketch though, you usually label them with the exact form. The square root of 5 is not only a surd, surds here are irrational. It's a non-terminating, non-repeating decimal. So you shouldn't really use up here a decimal form. That's an approximate answer to that. The most exact way of writing that is in the third form. Okay, I think you have the power. Let's go and use it. So remember here, key feature of the parabola, y-intercept, x-intercept, turning point of vertex, axis of symmetry, and just remember ax squared, hang on, let's do this, y equals ax squared plus bx plus c, that leading coefficient, if it is equal to naught, don't worry, there's no, that becomes linear, there's no quadratic function then, it's not a quadratic. If a is less than naught, that's a negative, remember, less than naught, then it is concave shape. Okay, if a is greater than naught, that's a positive, we say in front there, then it is convex or concave up. Okay, just remember that, some terminology there. Okay, let's go down and practice now and have a look. Sketching parabolas. I want you to do everything to these, just like we've been doing. You have the power. Remember, you have the power. Let's go and use it to pull all these apart and draw them at the end. Sketch the graph fully labelled. So this is the end of our section here. So just exercising our power here. So there's the answers for some of them. Let's go down and look at the next few down there. Okay, let's go on. Okay, question 2, same point. Find all of this, but they want you to use turning point or vertex form. So we want to change it using completion of the square. They might have to revise that. Do you have that power still? Okay, let's look at the answers then. Okay, to that bundle, so you actually have to complete the square first to get these turning points here, okay, or vertices. Okay, let's go on. Sketch the graph showing all the key features. So some other little ones, so we've done these before. So do a few of those and do a sketch. They're a little bit simpler because they've only got 2 terms in the expression. But think about that. What is the, let's say this one as an example. Can you say what the translation of x squared is to get that function? I think you can directly. Okay, let's have a look at the answers then. Okay, so they are the sketches. Make sure you've got all features correct. X-intercept, y-intercept, axis of symmetry, and the turning point, or the vertex. Okay, come on down. Next question, question 4. Putting you through your paces here. This is a review going right back to the beginning, where we're given the vertex or turning point form. All we got to do is sketch the graph, but we do want the y-intercept, all key features, x-intercept and y-intercept for these. Okay, let's have a look at the answers. Okay, fair bit of work there, getting all aspects there. Let's have a look at question 5. Sketch the graph showing all key features. So same thing again, more of the same. They're a slightly different bundle, this one. So x-intercept, y-intercept, axis of symmetry, and here are your answers. Let's see if we can get them all on. Yep. Okay. Notice they're not labelling the axis of symmetry. It would be good to put here x equals -5 as well. Okay. Let's go on to the next batch. Plenty of practice here. Okay, 6, 7, 8, getting into different format of a question. You can check those out. Okay, just doing bits and pieces. Y-intercept, x-intercept, seeing if you know that. Okay. All right. Let's have a look at the answers then. 6, 7 and 8. Did you get them right? Do you have the power? Okay, come down, and next level here of understanding, 9 and part of 10, so we'll have a look at 9. This is an applied problem, applying it to an actual problem. We know this is where the Greeks named or from which the Greeks named the shape of the graph as a parabola, because something was thrown. Parabola means thrown, and you're going to get the concave shape. Okay, remember that? Okay, let's look at number 10. Okay, number 10, you've got to match the equations there. Parabola A, B, C, etc. Let's look at 11. Oh, hang on, we've got a few here, I think. 11 through, I'm not sure whether it's 14. No, 11 through 13. Okay, again, an applied problem. Okay. All right, let's have a look at some answers then to all of those. There we are, we've got them all on one page there. Multiple choice questions here. Notice in this one, really should put x is equal to 3 as the axis of symmetry. Okay. Not so much in a contextual problem where you're using mathematics in a context. It's just a graph of temperature and what's h there? H is hours of time, yeah. So we really should label these axes with the units. Okay. All right, let's go and do the last one, the open-ended questions. These are all from Pearson's, of course. So I know we've got reasoning questions next. So you actually have to put your own function together here and here, make a model. We want to mathematically describe this application or this practical situation, so that's called modelling. When you write an equation, that's our mathematical description of the situation. Okay, so pause that. Let's now have a look at the answers. Okay, how did you go with that? Okay, do you have the power? Here we go. Last little batch here. The open-ended questions, let's go to 18. I think that finishes there. Okay, so have a look at the answers to those. They are open-ended, so there's a few different possible ways of stating them there. Okay, let's go and have a look at the answers to those. Sample answers. Okay, gives you a little idea of what you had to discuss there for each of those. All right, are you feeling powerful in quadratic function land? I hope you are, because we've done a lot of work on all aspects of the parabola. Very important shape, of course, as we started. And now what we're going to do is we're going to crank up the calculator again. The batteries aren't flat anymore, and we're going to see what technology has to offer in the final presentation on the quadratic function with technology. So I'll catch you then. Cheers for now.